All right, so we've talked a little bit about the properties. Let's go on into the formation of glasses. And so to talk about glass formation, what we end up talking about is nucleation and growth, or the formation of crystalline solids. Because if we can study how crystalline solids are formed, we can try to suppress that, right? And that's what we have with amorphous materials, is we try to avoid nucleation and growth. And so that's what we're going to study in this module. All right, so to do this, we have to look at the thermodynamics. So if you might need a bit of a review, but I'll try to give you a bit as we go along. So what we're looking at here is temperature on the x-axis and then free energy on the y. And just as a reminder, before we get into thermodynamics in more detail in a coming chapter, free energy is basically telling us about favorability in a reaction. So the lower the free energy, the more favorable the material is. And so the critical temperature here, if we're looking at a solid formation, is the melting temperature. So above the melting temperature, in temperature, we see that we have the free energy curve for solid crossing the free energy for liquid. So at the melting temperature, they're the same. So they're both in equilibrium because they're both the same. But at the higher temperatures, the free energy of the solid is higher than the liquid, which tells us that this material would like to be a liquid, right? And that's what we typically see at those temperatures, is a liquid. However, when we go to the other side, we see that they cross and go the opposite way. So now the liquid is at a higher free energy and the solid is at a lower free energy, which again would tell us that the solid is the favorable phase. So based on this thermodynamic argument, the solid is going to be more stable and tends to form below the melting temperature. And the gap between the two curves expediates or gives us a driving force for the nucleation. So the more and more different they are, the higher and higher the driving force for this reaction to occur. So that's what we see here, and that's what the volume free energy term is. It gets bigger as the temperature gets lower, as the undercooling gets higher. So the undercooling is the delta, the difference between the two temperatures. So we just talked about that volume or bulk free energy, but we also have an additional term, the surface, right? Surfaces are unfavorable, so the volume decreases the free energy, which is good, but the surface energy, anytime we create a surface, that is expends energy, it increases the energy of the system, right? Having a surface between a solid and a liquid is unfavorable, and so that increases the energy. So if we combine these two, it gets us to the total free energy of this reaction. And what we see is that we have going from, this is talking about a nucleus of the solid as it changes the radius. So this is r, the radius of the solid particle in the liquid. And so what we see is that basically we go from not having a solid particle over here at 0 to increasing that solid particle. And we see that initially making a solid particle of a certain size expends energy into the system. And then it reaches a maximum though. And at that point, it goes down. And so since we have a maximum, a local maximum here, we call this the critical radius, because essentially once a solid of a particular size crosses this threshold, it is now stable because it reduces the energy of the system to make it larger and larger. So that's what we basically have a critical point here. And so this is our critical size. We call it at that point an embryo. And it's at that point, it's more like it's critical, it's stable. If it was under that, it would be more likely to redissolve than grow. So this is kind of our critical point. Below it, I believe I used the wrong terminology, but below we call it the embryo because it's not yet sort of stable. But then once it reaches that critical size, we call it a nucleus or nuclei. So that's the kind of critical point that we have. And so that's the important part for making this solid, crystalline solid. All right, so if we look at different curves, if we change that undercooling, so basically if we, this is a small, if we're at a temperature here that's just under the melting temperature, that has a small undercooling because we're talking about Tm minus T. Whereas if we're way down here, the undercooling, as we're calling it, is large because the difference is large, right? So that's what we're talking about with the undercooling here. So what we see is that undercooling has an effect on the shape. So for small undercoolings, the critical radius is quite large and the energy barrier is high, right? Because this is the positive axis. So it takes a lot of energy. But once we cool to even lower temperature, so we have a larger undercooling, you've seen that the radius decreases and the energy barrier that we have to cross to get a stable nuclei is lower, right? So that's the driving force. The effect of that driving force is to lower the energy barrier and make the radius term smaller. So that's really important for us. And this is where that temperature comes in when we're talking about this critical. So if we want to calculate this critical value, which is the peak here, we can do it with this term in here. All right, so that kind of talks about the formation of a nuclei, and so now let's look at to do that and to form atoms onto that nuclei. We have to look at atoms going from the liquid to the crystal, and so we can view that in this way, right? So this is our solid nuclei. It's growing, it's trying to grow, so there's an interface that's growing. And so we want to look at atoms attaching to that crystal across that barrier. And so the barrier is here. It's basically shown as free energy. So you have an atom at this position, and it must overcome this peak to go to the solid, which is down here. So you can see that delta GV, that difference in volume free energy, is what we've talked about already, right? So going from a liquid to a solid reduces the free energy. However, moving that atom from the liquid to the solid takes an energy to migrate it, to move it. And that's what this delta G M star is. So the M stands for migration. And so that takes thermal energy, right? If I want to move an atom in the liquid to the solid, I have to have some thermal energy to move it, right? To do that. And we can describe that, we can describe that frequency of a jump across the interface by this equation here, which accounts for the migration free energy as a function of temperature. So we see the sort of classic exponential form here. So this attachment is going to be faster at higher temperatures, right? So here we see a sort of a classic competition between sort of kinetics and thermodynamics happening to the nucleation rate. So if we want to study the nucleation rate of a solid, right, because we're trying to study how glass is formed, and glass is not a crystalline solid. So we want to basically eliminate the nucleation rate. And so this will help us understand that. So we have this classic, if we want to study the nucleation rate is a sum of the two terms we just talked about. This migration that we just talked about, where the more temperature we have, the more atoms can cross the interface. And then the other thermodynamic term in which the free energy was greatest when we lowered the temperature, right? More undercooling. And so this is kind of a classic competition between what I term the kinetic barrier and what I term the thermodynamic barrier. So this migration term increases with increasing temperature. This migration term um, increases with decreasing temperature. So they have opposite effects. And so what happens there is that one of those is going to be the rate limiting factor, right? So let's think about it in terms of the temperature here. So if we go to a really high temperature, right, it's really close to the melting point. So there's no barrier. There's no driving force based on the thermodynamic term, right? Because we wanted something really far away from the melting temperature at a much lower temperature. So at the very highest temperature near Tm, the barrier there is very great. And so that limits the overall reaction, even though the kinetics are best at the highest temperature. So this limits the reaction. And vice versa, at the lowest temperatures, that driving force is highest, but it's the lowest temperature, and kinetics, the diffusion at those temperatures decreases rapidly. And so diffusion kind of rules out the kinetic barrier, makes it zero. So what we need is some intermediate. So we need some mixture in the middle, and that's where we get the max nucleation rate, because we have a moderate kinetic barrier and a moderate thermodynamic barrier. And so the intermediate temperatures always give the max nucleation rate. So this is important, right? Because if we can eliminate time in this temperature range, then we could potentially limit the formation of crystals, which is what's important for glass. So we either need to be at the very high temperatures, or we need to be at the low temperatures to try to block out the movement of atoms. All right. So we've talked a lot about this nucleation, and in general, that nucleation was what we call homogeneous nucleation, where we had a spherical particle form from the bulk of a liquid. However, heterogeneous nucleation is far more sort of technologically important, and that's where we nucleate a particle of a solid at some type of interface or on some type of surface. So it could be a free surface. So this is a particle nucleating from a surface. It could be from a pore or some type of interface. So this is nucleation of water gas, or just gas in the water on your finger, which is an interface. It could be from a pore. It could be a grain boundary, or it could be a dislocation, right? There's lots of different places, but it's some type of interface or surface. So this is more important technologically, and this is what happens in a majority of cases throughout this field. So this heterogeneous nucleation modifies the energy, the nucleation rate, and so we have to, and that's based on the contact angle. So whether you have something like this, where you have a water droplet. So it's basically it's not even really on the surface. Or you have this case where it kind of beads up and forms a droplet. Or over here to the other extreme, where you have a low contact angle, and it spreads on the surface. And so there's a lot of surface between the liquid and the solid. So basically, this likes the surface, this really hates the surface. And so that modifies the barrier to nucleate something. And so as this decreases, as the contact angle decreases between these two surfaces, the barrier to nucleate also decreases. So having something that wets a surface helps the formation of these solid particles. So that's also useful to know, right? Because we want to avoid those situations when we're looking at glasses. All right. And we've talked a lot about this nucleation now, so I want to sort of get into the growth side of it as well, because there's always a component of growth that we have to talk about. And we tend to define growth based on entropy. And so in this case, we have a very rough surface, which is a rough solid liquid interface. And because it's very rough, the entropy between the liquid and the solid is quite small, the difference in entropy. So the delta S is small. And so what happens here is that the surface is very rough, and there's lots of little places where a liquid could attach to the solid, right? So all of these little contact points are places where the liquid can attach to the solid. And so it tends to happen quite uniformly, and so it grows out from the surface, so perpendicular to the surface, as you can kind of see here. So this is known as standard growth, and it happens relatively fast. The other type is where we have a very different entropy between the surface of the solid and the liquid. And so this is where things are really smooth, right? We have a really smooth surface, and so the difference in entropy between the liquid and the solid is much different. And so in these cases, there's not a lot of places for an atom to attach and attach to the surface. So it has to do it on these very kind of unique sites. So for example, if we have a solid that has a dislocation in it, so here's the dislocation axis, and this is our screw dislocation. Basically, the atoms want to attach at the interface here, where it's coordinated by a lot of other atoms. It doesn't want to just grow on the surface very effectively. So there's very few places where a solid can attach, and so its growth is along that sort of axis that you see. And so growth here is very slow, and it's normal to that plane, and so different than the standard growth that we just saw. So this is very slow, and so that's another thing that we need to keep in mind when we're thinking about glasses, is controlling this kind of growth rate when we're looking at materials.